Hello, welcome back. So what we want to do is talk a little bit about resonance, and then review a little bit about waves, and get to some new material there. So first off, everything will oscillate with some natural frequency, meaning if I pluck it, strike it, hit it, it'll vibrate with some natural frequency or natural period. So, for example, the CNN tower in Toronto, the tip of this will sway back and forth about 3.5 feet in a strong breeze, and I guess this would be the observation deck. Would move back and forth about 1.5 feet in a strong breeze. So even things you don't think of as being terribly flexible, like concrete buildings, things like that, they are flexible, and they will vibrate and oscillate. So what we're covering is very, very applicable to a lot of the things you see around you. A lot of things will vibrate back and forth. So here I've got a video clip, I guess, of buildings vibrating. So you can see this building vibrating, oscillating back and forth. It must be due to an earthquake. Sways the building back and forth. So a lot of things will vibrate if perturbed. If perturbed. So and they will follow pretty faithfully what we've looked at before. The period, the natural frequency equals 2 pi to the root of m over k, where m is the mass and k is the effective spring constant. Now things naturally vibrate at a natural frequency. That just depends on how they were constructed, and you know how tall they are, how massive they are, and things like that. If you vibrate those things at the correct natural frequency, what you get is a buildup of the wave, or that of the oscillation. And that oscillation gets stronger and stronger and stronger, even if the thing doing the vibrating isn't that big of an oscillation. So just like being on a swing, if you pump your legs at the right frequency, that little bit of pumping action that starts very small at the beginning, you can swing almost up to even with the bar. So that's an example of what's called resonance, vibrating something at its natural frequency, and building up that oscillation. For those of you that are in person, I'll have a demonstration. If I forget to do it, remind me to do it. I've got a pretty cool little demonstration on resonance. But having the right frequency, matching that natural frequency, is important. And for example, if you produce a sound wave that matches the natural frequency of a wine glass, that vibration can build to the point where that glass will break. And this would be the effect of resonance on amplitude, as this is the opposite of a dampened oscillation. I forgot, I've got two demonstrations that have to do with the resonance. This one's pretty cool too. So this is a good thing if you're on a swing. It's not a good thing for structures. So the idea of resonance has got to be taken into account when you build things like bridges, and even in airplanes, where vibrations from flight can build up and could theoretically cause a wing to break off. Resonance is kind of a cool phenomenon in physics. So anyway. All right, on to mechanical waves. So like water waves and things like that. A mechanical wave carries energy through matter. So mechanical waves need material. The only wave that is not a mechanical wave is an electromagnetic wave, like light. Other than that, all the waves that we're going to deal with, need matter. So waves carry blank from one place to another, but not blank. If you look at one of these little circles, which is supposed to represent a particle of water, you see that the particle stays more or less in place. I mean, it moves in a circular pattern around its kind of home position, but it doesn't end up moving down with the wave. What ends up moving from one place to another is not the water. Okay, it's the energy that's being transmitted through the water, and that energy can be very destructive in a water wave, such as a tsunami or something along the lines of that. So I can send a wave or a wave pulse down some other material like a string or a spring, like a slinky, just by giving it a quick shake. Here's shown a wave pulse, which is just an up hump as opposed to an up and a down hump, which would be a full cycle. So if I make one complete jiggle, I get one complete wave that will travel down that material. And again, the spring, the slinky, doesn't end up all at one end. It's just the energy that moves from one end to the other. The material, the stuff, the mass, whatever that wave is traveling through is called the medium. That's a term you need to be familiar with. So it could be the water in an ocean wave. It could be the slinky. It could be the rope. It could be the earth in an earthquake wave. Any material that the wave travels through is called the medium. So what is normally the medium for a sound wave? The standard medium. That would be air. So air is the medium for a sound wave. If you continue to jiggle the end of that slinky back and forth, you'll get a bunch of crests and a bunch of troughs. And again, it's not the slinky that's traveling down that wave. It's the energy. It's the disturbance. So just a quick review on waves. So one complete cycle is an up and a down, or it could be from a crest to another crest. It would be a complete cycle. So just before it starts to repeat itself. The line traveling through the home position or the equilibrium position is known as the baseline. So the top of a wave is known as a peak or a crest. A trough is a low point, and any time that wave crosses or touches the baseline is a node. Okay. The crests and troughs are technically antinodes. Wavelength is the length along the baseline of one cycle. So it's one cycle, or it's from crest to crest or trough to trough. All waves, methods of measuring the wavelength. The symbol we use for wavelength is this upside down Y. It's called a lambda. But that is the symbol for wavelength, which will be measured in meters. The amplitude is the distance from the baseline to a crest, or the distance from the baseline to a trough. So, okay, here I've got a little applet that is from the PhET website, PHET. If you want to play around with it, just Google PhET waves, PHET waves. So what I can do is I can send a pulse down this medium, which is this string with little balls on it. And what I want to do is look to see the effect of how changing some things is going to affect the velocity of the wave. So check out the velocity of this. So as it travels down the wave path, not moving too fast. Let's try increasing the amplitude. Now, if we increase the amplitude, that's going to make a taller wave. Predict how that's going to affect the velocity of the wave. Now, we probably should be timing this. I guess. Where's the timer? Okay. How do I time and hit the pulse? This gets to be a little tricky. Yeah, I probably really can't. So let's do a taller wave, and let's just qualitatively look at see how it affects the speed. So, looks to be pretty much about the same. So that taller wave and the shorter wave looks to be traveling down the wave pretty much the same speed. So it doesn't look like amplitude really affects it. Let's put it on oscillate. So let's get a wave. So what I can do, I can actually time this one. What I'm going to do is time I can put it in slow motion too. That's going to take a long time to do. Let's do it normal. So I'm going to time the time it takes for a crest to go from here down to and meet the window, the frame here, and then we're going to test the effect of changing the frequency. So right now the frequency is 1.5 hertz. I can increase the frequency to 3, or I can decrease the frequency to 0.3. So we'll put it back to 1.5, and let's get my stopwatch here. So we'll start it now. So this is the one we're measuring. Okay, so it was about 6.43 if I did that correctly. I should probably do that a couple times to get an accurate reading, but we'll say about 6.5 seconds. So let's increase the frequency. So predict how that's going to, oh, that's the amplitude. Predict how that's going to affect the frequency of the wave. Affect the velocity of the wave. Is it going to travel faster, slower, or be the same? Okay, so I'll increase the amplitude, and then this is going to be hard to follow. So this will be approximate. So and 1. Okay, so it was about 6.4. So it looked like it was about the same. So so it doesn't look like frequency affects the period or the velocity of a wave. What the wavelength or what the frequency does affect is the wavelength. Okay, so if I have a wave like this, if I decrease the frequency, that wave gets longer. And if I increase the frequency, that wave gets shorter. So the wavelength and frequency are related, but they don't affect the velocity of the wave. Now what does affect the velocity of the wave is the medium. Whoops. If I increase the tension in this rope, in this spring, it'll actually increase the velocity. Okay, so now if I were to time it, it would be only a couple seconds. So the tension, the medium, does affect the speed of the wave. So all right. So one thing you want to make note of is the only thing that affects the speed of a wave is the medium. The only thing that affects the speed of a wave is the medium. Okay, now how would you measure the period of a wave? Okay, well, what I would want to do is take a convenient measuring point, so say this line, and then I would start my stopwatch when, let's say, a crest reached it, and then I would stop my stopwatch when the next crest came by. So I would do a start and then stop. That's how you measure the period of a wave. No different, really, than measuring the period of a pendulum or a mass on a spring or anything along those lines. Okay, how would you measure the frequency of a wave? Well, that would get a little harder. You'd have to time it for some time, let's say 10 seconds, and count the number of waves, and then divide to figure out the frequency. So, but what you're looking for is the number of waves that pass by each second, and that's the frequency. Okay. Now, how would you find the speed of a wave? Well, you need to know the distance and the time that the wave traveled. Okay, what would be a convenient time period to measure? Let's go with the period. Okay. Well, how far does the wave travel in that given amount of time? Well, it travels one wavelength. Okay. So speed is equal to wavelength divided by period, or lambda over t. Okay. So V equals lambda over t. Now we're not going to use the equation in this form very much. Okay. This is the form of the equation that you really want to jot down. Since frequency equals 1 over t, Okay, we can take this 1 over t and just make it lambda f. Okay, and that's the form of the equation that's more widely used. So v equals lambda f. The velocity of a wave is equal to the wavelength times the frequency of the wave. So that one you do want to have jotted down. Okay, so let's say you're standing on a beach and you measure the distance between crests to be 1 meter. If 3 waves pass you each second, what is the wave speed? Okay, well, we're looking for velocity. We want to know wavelength. Well, that's that 1 meter. And we want to know the frequency. Well, there's 3 waves per second. That's my frequency. So it's just 1 times 3 gives me 3 meters per second. Now, that would be meters per second because this is wavelength is in meters. And frequency is 1 over seconds. Okay, so it's meters per second. Okay? Now, if the wavelength is the same, what happens to the frequency if the wave travels faster? Okay, so if the wave speed increases, okay, and the wavelength is constant or is the same between two things, is the same, what happens to the frequency? Well, we can look at our picture and say, oh, this wave is traveling faster and I'm getting more waves per second, so that means I have a greater frequency. Or we could have looked at the equation and said, well, if I make this bigger, okay, then this side of the equation's got to get bigger, so that frequency is going to have to increase. Okay? V equals lambda f. What does this slide illustrate? So what's the same between these? Well, the velocity of these waves is the same, okay? But the wavelength is much shorter here, okay? And if the velocity is the same and this decreases, then this has got to increase. Okay, so basically, as we decrease the wavelength, I'm getting a lot more waves pass by this point per second than I am in this wave. Okay, V equals lambda f. Okay, so if your velocity is constant, if your wavelength decreases, your frequency increases, and vice versa. If you increase your frequency, your wavelength decreases. Okay. So, so let's see. So if the speed is constant, if my frequency goes up, then my wavelength will what? So if my velocity is constant, if my frequency goes up, then my wavelength will do what? It will decrease. Okay. Let's say my frequency is constant, and my wave speed goes down. So if my wave speed goes down, what's going to happen to this? Well, this is going to decrease as well, just using this equation. Okay. How does the amplitude affect the speed of a wave? It doesn't. How does the frequency affect the speed of a wave? It doesn't. Okay. What determines the speed of a wave? Only the medium. Okay. The only thing that affects the speed of a wave is the medium.